Real-world lighting often consists of multiple illuminants with different spectra. Separating and manipulating these illuminants in post-process is a challenging problem that requires either significant manual input or calibrated scene geometry and lighting. In this work, we present a method to separate a single image captured under two illuminants with different spectra into the two images corresponding to the appearance of the scene under each individual illuminant. For a scene illuminated by two lights, the captured image is the linear sum of each single image under a single light source. In this paper, we aim to invert the process by separating the observed image into two images, each only illuminated by a single light source. However, this is a very challenging problem. The image intensity observed is a complex function of a reflectance, illumination, and geometry, making the problem highly ill-posed. To solve this problem, we train deep neural network to predict the per-pixel reflectance chromaticity of the scene, which we use in conjunction with a previous flash-no-flash image-based separation algorithm to produce the final two output images. In particular, our network consists of three subnetworks that produce the reflectance chromaticity, illuminant shadings, and the separated images respectively. We supervise the outputs from three subnetworks. To generate the training data, we first utilize the data generated with physical-based renderer with ground truth. Given the input image, we compute the reflectance chromaticity by using the provided ground truth reflectance in the database. Next, we solve for illuminant shadings, as well as the separated images by using the method of Hui et al. We also include the real captured data by using flash and no flash. To obtain the reflectance chromaticity, we subtract the no flash from the flash and compute for the color chromaticity. Similar to the rendered dataset, we use Hui et al. To generate ground truth illuminant shadings and separated images. Now, let's see the performance of our technique under real-world scenes. Here is a scene which is illuminated by outdoor illuminants from the windows, while being illuminated by the warm indoor light on the top. This is the separated image for the outdoor illuminant with cool color. We can clearly see the shadows on the small couch, as well as those on the side of the near chair, which are closely resembled to the manner of the outdoor light. And this is a corresponding separated image by the indoor light source. For the indoor light source, we can clearly see the shadows on the wall in the far end. From these separated images, our method is able to capture both the color and shading for each of these sources. Here is another scene which is illuminated by outdoor illuminant from left, while being illuminated by the lamp on the right. This is a separated image for the outdoor illuminant with cool color. There is no shadows appear near the keyboard and the mouse, since skylight is an area light source. For another image with respect to the lamp, we can observe clear shadows appeared near the keyboard and the mouse. Now, let's look at another example. This scene is captured after sunset, and it is illuminated by outdoor light source with warm light from the left, and the skylight from all the directions. The skylight is the area light source, which does not introduce shadows in the scene. As expected, our separated image for the skylight exactly matches the manner of the light source. For the outdoor illuminant, we can clearly see the highlight from the light and shadow on the tables. Compared to the past technique solving a similar problem, our technique only requires a single photograph. For the method of Hui et al., which relies on a pair of flash and no-flash images, it produces artifacts since the flash is not strong enough to illuminate the scene points in the far end. In contrast, our method does not require flash image and is able to produce high-quality results, making it more practical for real-world applications. We can also apply our method to outdoor time-lapse video, where it is often necessary to separate direct sunlight from indirect skylight. As can be seen, our technique is able to produce the sky illumination results without shadows and attribute cast shadows to the sun illuminated images, both of which closely resemble to the manner of the sky and the sun illumination. In our work, we address the highly ill-posed source separation problem via the use of a single photograph. We show that we are able to produce high-quality outputs that match the performance of previous methods that required a flash-no-flash pair, while being more practical in requiring only a single image.